Another way of a state space representation is by using canonical form. So in canonical form representation, again there are two types. One is a diagonal canonical form, the second one is Jordan canonical form. So they look same, the diagonal and Jordan, but Jordan is a special case of the diagonal canonical form. Let us see how to get this kind of forms whenever the transfer function is available with us. Now let us take the transfer function in polynomial form as y of s by u of s, where y is output, u is input, is equal to, it is a ratio of polynomials. So numerator I can take it as a bn s power n plus bn minus 1 s power n minus 1 plus dot 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 up to b naught. So in the denominator we have s power n plus a n minus 1 s power n minus 1 plus dot dot up to a naught. So this is the transfer function which you are taking, and we are trying to convert this into diagonal canonical form. Now in diagonal canonical form, the ratio of two polynomials is converted into the factorial form. Once the factorial form is available, then we can easily draw the block diagram, and from the block diagram we can derive the diagonal canonical form. Let us see how to do that. So let us assume your order of the system n is equal to 3 for simplicity purpose. Therefore y of s by u of s becomes you have b3 s cube plus b2 s square plus b1 s plus b naught. So in the denominator we have s cube plus a2 s square plus a1 s plus a naught. So this is the transfer function when n is equal to 3. Now this transfer function I want to convert into factorial. So what I can do here, let us say a denominator I can write it as s minus lambda 1, s minus lambda 2, s minus lambda 3. So since the order is 3, assume that all three roots of that equation are in this version. So lambda 1, lambda 2, lambda 3 are nothing but the roots of the denominator. We know that roots of the denominator are the poles of the system. Now I want to again get the C1, C2, C3 which are the residuals of the numerator for the corresponding factors lambda 1, lambda 2, lambda 3. So if you do that, let us say I am writing it as y of s by u of s is I am getting a constant b3 plus there is a coefficient, residue coefficient c1 by s minus lambda 1 plus c2 by s minus lambda 2 plus c3 by s minus lambda 3. So c1, c2, c3 we can easily find out by using the factorization. Now, so it is y by u or y of s by u of s. I just want to multiply u to the other side. So what will be the output in this case? The output is nothing but b3u plus I'm writing it as a 1 by s minus lambda 1 into c1u plus 1 by s minus lambda 2 into c2u and the plus 1 by s minus lambda 3 c3u. So this is the equation. So once this equation is ready with us, then I want to draw the block diagram. So we have only one equation, but in this equation there are 4 terms, and how to get those 4 terms. Let us take the output y is here. Now the equation output has a different terms, therefore I need to add all the terms. So before y, then I have the summing point. So to the summing point I need to have all the branches which are coming. So I am taking input u here. Now first one is u into b3. So u is there, then directly I am taking a block, its gain is b3 and I am connecting to one of the inputs of the summing point available at the output side. Next is, now I want to get 1 by s minus lambda 1 into c1 u. So u is available, I can take u. So s minus lambda 1 by s minus lambda 1, I want to rewrite it as or re-represent it as a feedback loop. So how can you write that? So again I am taking a summing point, then this is my integrator, then after the integrator then I am taking the feedback here, that feedback is minus lambda 1 and I am going to have the negative feedback. So I am taking the integrator. So if at all if you have any first order term, then certainly we can represent with the one integrator and its corresponding loop. So that is what I am doing here. So one integrator and there is a loop with the lambda 1, and that is multiplied with the residual constant c1 and it is given to one of the inputs of the summing point. Similarly the third one, we have 1 by s minus lambda 2 u c2. U is already available, anyway c2 I will connect here later, and this is again the similar way. I will take one integrator and I'll take the feedback with minus lambda 2, I can connect it negatively. So this way I can connect. And finally we have another one, we can also connect 1 by s, and this is lambda 3, and there is a negative feedback, and after that we have a constant C3 that is also connected to the summing point. Now all the integrators are connected in this case parallel, therefore it is also called a parallel decomposition method. So both the diagonal method as well as the Jordan methods are called parallel decomposition. So now for each integrator, we know the output of the integrator is a state variable. The input to the integrator is a derivative of the state variable. So I am taking this as x1 and this is going to be x1 dot. And for second one x2, x2 dot, x3, x3 dot. There are 3 state variables because there are 3 integrators. Now to get the model, write equations for derivative of the state variables. When you write equation for the state variables, then we can easily represent in matrix form, which will be the state model of the system. Now by looking at the block diagram, then we can write equations as x1 dot is equal to, there is a one input which is u is coming and there is a one feedback which is coming, therefore u plus lambda 1 x1. Similarly second equation x2 dot is, again we have u plus lambda 2 x2, and third equation x3 dot is u plus everywhere we have u because we are taking the same inputs, so therefore x3 to lambda 3. So with these 3 equations, then I can write the state model as this is state vector, derivative of the state vector x1 dot, x2 dot, x3 dot is equal to, we have the matrix form, then after that x1, x2, x3 plus input matrix and u. So we have only one input u. Then what are the entries? If you look at the equation, it's very clear. So every term you will be having only one term and the remaining is u. Therefore the B matrix is 1, 1, 1. In all equations we have u, therefore the B matrix is all 1. Then what will be this matrix? So in the first equation we have x1 coefficient, lambda 1 x1. Therefore lambda 1 is the first element, remaining all zeros. The second is lambda 2, second element, all remaining zeros, and third is lambda 3. So this lambda 1, lambda 2, lambda 3 are the diagonal elements of A matrix and remaining all zeros. So this A matrix purely a diagonal matrix. That is the reason why this model is called diagonal canonical form, where your A matrix is the diagonal matrix. And one more important thing is the diagonal matrix, the diagonal elements are nothing but my poles of the system. Hence I said A matrix is called system matrix or state matrix, which is very important in the analysis of the any control system. Right, so what will be the output matrix? So output we can write directly as, because we have C1, C2, C3, so we can write with the help of C1, C2, C3, y is equal to C1 x1, C2 x2 plus C3 x3. And also we have B3 u. So 4 inputs are there, those 4 inputs you can put in a matrix form. So y is equal to, we have C matrix as C1, C2, C3, and D matrix is, of course it is B3. So this is the state model in diagonal canonical form. So what is the use of this form? So using this form, then we can find out the stability of the system, because A matrix, the elements are the poles of the system, poles are readily available. Since the poles are readily available, we can easily obtain the system stability.